Welcome to lesson 3.8, perpendicular lines. So we've already looked at the idea of parallel lines being lines that are on the same plane and never intersect. And again, we know parallel lines have different y-axes, or different y-intercepts, I should say, different y-intercepts, but the same slope. Now, today we're going to move on to perpendicular lines. Perpendicular are two segments razor lines that intersect to form exactly a 90-degree angle. So they can be segments, razor lines, intersect to form a right angle or 90-degree angle. So then these bullet points below are 4 important things to keep in mind related to perpendiculars. So in the figure at the right, ABC is a right angle. So A to B to C is a right angle. We know that from the 90-degree right angle symbol, this little square in the corner. So if ABC is a right angle, we know lines M and N are perpendicular. Now the symbol for perpendicular is this upside down capital T. So you can write M perpendicular to N to show the two lines are perpendicular. We cannot assume that drawn lines are perpendicular unless they mark it with a 90-degree symbol or a 90-degree measurement, or we're told in writing that they are perpendicular. And then when intersecting lines form one right angle, the other 3 angles formed are also right. So this angle is a right angle, meaning this one here, down here, and over here are all right angles. Then we move into one of our 3 different theorems. The first theorem that we're going to look at is the two perpendiculars theorem, which states if 2 coplanar lines, L and M, are each perpendicular to the same line, then they're parallel to each other. Now in my example, I used 2 different lines. So I used M and N. So if M and N are both perpendicular to L, so if M's perpendicular to L and N's perpendicular to L, then we know M is parallel to N. The perpendicular to parallels theorem says in a plane, if a line is perpendicular to one of 2 parallel lines, then it's also perpendicular to the other. So in this case, if we look at this diagram over here, if I was given M and N are parallel and L is perpendicular to M, then I can also say L is perpendicular to N. And our third theorem, the perpendicular lines and slopes theorem, states if 2 non-vertical lines are perpendicular if and only if the product of their slopes is -1. So if we multiply the 2 slopes together and they equal -1, those 2 lines are perpendicular. If they equal anything else, then we know those 2 lines are not perpendicular. So slopes that would make a line perpendicular multiply to be -1. So an example would be like 1/3 and -3/1, or 2/4 and -4/2. Multiply those together, and both times you get -1. So now we're going to apply some of these theorems and rules to our examples below. Example 1 asks us to find the slope of a line perpendicular to the line y equals -2/3 x plus 7. So remember, your slope's always attached to x. Oops, didn't mean that. Slope's always attached to x. So in this case, our slope is a -2/3. So what we want to think is -2/3 times x, or what? would equal a -1. So we're trying to figure out what our missing slope could be. So a -2/3 times what equals -1? So technically we're taking a -1 divided by a -2/3. Well, dividing by a fraction is the same as multiplying by the reciprocal. So a -1 divided by the -2/3 is a -1 multiplied by a -3/2. So that tells me my slope of a line perpendicular to this equation here would have a slope of 3/2, because 3/2 times -2/3 is -1. So in example 2, now they want us to write the equation of line L that passes through the point 2, -3 and is perpendicular to the line y equals 4x minus 1. So the first thing we want to do, again, if we're dealing with perpendiculars, is find our new slope. So the current slope was 4, or 4 over 1. So we're trying to figure out 4 over 1 times what equals -1. So a -1 divided by 4 gives me that missing slope. So my slope is a -1/4. So I have my perpendicular slope. What I don't have is the y-intercept, so b. So if we're using y equals mx plus b, we're going to set that up with our new slope, and we're going to plug in the x and y coordinate they gave us to solve for b. So we'd have y equals a -1/4 x plus b. We're going to plug in the two -3 for x and y to solve for b. So it becomes a -3 equals a -1/4 times 2 plus b. So -3 equals a -1/2 plus b. So we're going to add 1/2 to each side to solve for b, and b is a -2.5. So then we have our y-intercept and we have our slope. Now we can write our equation. Y equals mx plus or minus b, so y would equal -1/4 x minus the 2.5, because remember the m is always your slope, the b is always your y-intercept. So in order to figure out the slope of a line perpendicular to something, you need to remember the rule that the products of the slopes equal -1. We have our three new theorems right here to go with, and then the examples for finding the inverse or perpendicular slope, and the example for going through the 3 steps to rewrite an equation that's perpendicular to the one you were given. So as you go through this, if you have questions, let me know. And then the box at the bottom here is a table layout comparing Euclidean synthetic geometry in the left column and Euclidean plane coordinate geometry in the right. So when we're looking at the idea of a point, in synthetic geometry, a point's a location. In coordinate geometry, it's an ordered pair x, y. In synthetic geometry, we just draw what a line looks like. In coordinate geometry, we have standard form and different equations to get the line. The measure tilt of a line, so measuring that tilt of a line, in synthetic geometry, it would be an angle measure. In coordinate geometry, we calculate the slope. Then if we have parallel lines in synthetic geometry, we know the corresponding angles are equal. In coordinate geometry, the slopes are equal. And then finally, perpendicular lines, which we added today. We know in synthetic geometry, they're lines that form 90-degree angles. In coordinate geometry, we can figure it out because the products of the slope is a -1.